Good evening, everyone. Today, I'll be walking you through to how you can create your own GPT or like nano version of your GPT using this particular collab. So what we did is basically we followed this YouTube tutorial by
and then they can use it to.
him, Andrej Karpathy. He has a GitHub repository on the code. I just have like a better version with my own data and like some comments over there. But you can go check out this video first to get an idea of what the code is doing. He explains it pretty well. Now coming back to my code. So first thing, I also have published a Medium article for the same. Let's go to the Medium article actually. So first thing is creating your own GPT. What GPT stands for is Generative Pre-trained Transformer. What it does is given a particular word, it will try to predict what is the next possible word. So word is more of a complex version. We can look at a simpler version by looking at in a particular sequence what the next possible character will be. To train these, first the transformers are trained on a large chunk of data. For our instance, the GPT is trained on possibly all the data that is there on the web till 2021, like depend on the model you refer to. But for us, what will we do is we'll use that large corpus as one of the books by William Shakespeare. We'll be using the As You Like It novel. The only reason we are using it is because I know that novel. I read it when I was in school. That's primarily the reason we are using it. So yes, you have the full text version on this website. Okay, where is it? Yep, you have the full text version. You can just copy it and paste it as a simple text. No fancy data pre-processing required. Coming back to our Medium article. So now what we're going to do is we're going to use this large corpus, train our model on it, and train a model to predict, train a transformer to be precise, to predict the next character in the sequence. Now, first is we'll be using the PyTorch module. Just make sure you have it installed. We have our data saved in a text file if you're going to read that. And next, we look at encoding. So similar, if you have worked with any NLP stuff before, like computers don't understand characters. They have to be number. So what we do is we make sure that each character represents a particular number. The process when we take a number and make it represented we take a character and use a number to represent it. This conversion is encoding. And when you take the number and get it back to a character form, that is decoding. So basically what you do is you just get set of text that will give you all individual like unique characters in your like file. You make that as a list and then you sort it out, and then and the number of characters is your vocab size. Now you have a map which is string to integer, which is like the character to I map. And then you have inverse string to integer to string map. This will be the one you use for decode. And then you just create a lambda function which is like encode and decode. It just looks up the value and returns. Looks up like in that dictionary, it will look up the key and return the value. This is the simplest form of encoding decoding you can do. But yeah, let's go forward for it. Now we have a data set which is we just firstly we converted to a torch format so that it is easier for us to perform training on it when we use neural networks, specifically because we'll be using GPU. So tensors have default support in GPU. Like it makes the training much faster. So it's better to have them in the form of a tensor. So we converted it to a tensor. We have n is the first 90% of the data. So that is 19 to n. This is the number of data we want. So this would be a character split, basically the first this many number characters and so on. And the validation is remaining next. Now, if you know, we'll have a batch process. So we need something that can load the data in batch. So get batches if the data is trained or based on if the data is split or trained, it will like generate like a random index. It will take a random index from the entire pool and give it as a batch. And the batch size is something we have already defined in the hyperparameter set, which is you can find it over here. The batch size is 16. So that is 16 characters. Copy this and just give me a second. Oh, this- It should be fine. Now, once we have that, we just create an loss function and we do a manual loss calculation. This is just for not tracking the gradient so that we can test the model's performance anytime. Now let's look at the transformer. The transformers are built from a few components: the token embedding, the self-attention, the feed forward layers, and positional embedding. Now, attention mechanism is transformer superpower. At the heart of every transformer lies the attention mechanism. Imagine reading a sentence. Your brain selectively focuses on the words that matter the most for understanding. Attentions allow transformers to do the same. In simple terms, query is something what we are looking for. Key is what each word or character offers. Value is the actual content of each word or character. The model calculates the attention core to determine which part of inputs are relevant. Self-attention basis. So we have a head class which implements a single attention head to focus on different parts of the input. The key concept is you have key, query, and V, and then you have masking. A triangular mask ensures that the model does not attend to future tokens, preserving casualties. The weighted, and so this is how you have like a simple init function. You have query value and then register buffer. This is the till, which is the weighted mask, and then you have the feed forward. Then you have a multinet. Instead of a single attention head, multi-attention utilizes several heads operating in parallel. This empowers model to capture diverse relationship between tokens. So it's just a better, it's like a more complex version of it. You have a similar fashion over here. Your forward is the standard feed forward neural network, where you define your neural network, which is like a linear layer with with this input size, a ReLU activation, again a linear layer, and then you have a dropout layer. Then you have a transformer block. Transformer block is a foundational unit of it alternates between multi-head self-attention and feed-forward network. Now residual connections. So this is how you connect everything together. First you have your feed forward, then you have your multi-head, then you have feed forward. This is the main block, right? Then you have another layer normalization, near normalization, and then you have a forward, which is you first get the output from multi-health self-attention and then from the use that in addition with that of feed forward. Then we have bigram language model. So this is basically encoding and decoding. So what you do is token embedding table, we generated the embedding. You have the forward where you first take the input, you get the embeddings, you get the token embedding, you get the position embedding, and then you pass it through your whatever model which we created earlier. So if you look over here, we will have a transformer block somewhere around. What is the class called? Block. Okay, let's look for block over here. You'll have a block somewhere over here, self blocks. Sequential, so you have multiple blocks for each layer and so on. Now you have your training where for each iteration, we have defined the iteration earlier. We have the main model. We send it to CUDA device. We have figure out how many parameters are there to be trained. We use the IDMW optimizer. We have a number of iteration. For each iteration, we like just perform the training. We get the train batch. Using our get function, we get the loss and then we start again. This is how the training output looks. We trained for about 5,000 steps. And then we can just generate a random context and then print it, like ask it to it's basically predicting what is happening afterwards. Right. So context is there's nothing but like what happened earlier. Nothing happened earlier. So we just wanted to randomly generate. This is your embedding form. It could be like anything. So initializing the type, symbolizing the beginning of a text. So you can have any other particular sequence. You can have like a string of characters, encode them, and then pass it, and it could generate, okay, what will happen after this is follows. And this the model is generating considering it's like a new thing from the beginning. That's it from today's class, that from today's presentation. Thank you.